NASA's Space Launch System has once again run into fuel leak issues during its wet dress rehearsal, a problem that has become all too familiar, having surfaced multiple times during the Artemis 1 campaign. And because this is the very first crewed mission of the Artemis program, that naturally raises some serious questions. Has NASA actually made the necessary changes to SLS to make it truly ready for astronauts? How is the hardware on Artemis 2 different from what flew on Artemis 1? And why does the SLS fall so far short when you put it next to SpaceX's Super Heavy? Let's break it all down in today's episode of Alpha Tech. Recently, Artemis 2's Wet Dress Rehearsal, or WDR, ran into a fuel leak issue that immediately raised concerns about the mission schedule. At first, the fueling process went smoothly. Both the core stage and the upper stage were fully loaded and transitioned into replenish mode to maintain stable propellant levels. Everything appeared to be right on track. Then came the problem. Engineers detected a small liquid hydrogen leak at the tail service mast, umbilical interface on the core stage. The moment the leak was confirmed, the fast fill process was halted immediately. For hours, all eyes were on the pad as teams worked under intense pressure, troubleshooting the issue and searching for the root cause. After a long, intense investigation, engineers were able to pinpoint the source of the leak and bring it back within allowable limits. Crucially, the situation did not require rolling the rocket back to the vehicle assembly building, nor did it demand any major hardware repairs. Next, the closeout crew entered the White Room and carried out the full set of procedures' final inspections, closing and securing the Orion hatch and sealing the launch abort system. Once everything was verified and the spacecraft was confirmed to be safely sealed, the team cleared the pad according to standard protocol. However, due to the leak, the vehicle was safed and fully detanked as a precaution, forcing NASA to scrub the wet dress rehearsal. As a result, the Artemis 2 launch date is now expected to slip by at least a few days. Now, because this is only the second flight in the Artemis program, a lot of people are naturally wondering, did NASA actually change anything on the Space Launch System? That's a fair question, especially when we're used to seeing rockets like Starship evolve rapidly from one flight to the next, learning from failures and getting upgraded almost every time. But in the case of SLS, Artemis 1 performed remarkably well. So well, in fact, that NASA decided to keep essentially the same Block 1 configuration for Artemis 2. And if this upcoming mission goes smoothly, that same design could even carry over into Artemis 3. NASA has already completed the design of the more powerful Block 1B variant, featuring the new exploration upper stage, but that upgrade isn't expected to fly until Artemis 4 and beyond. So, let's take a closer look at SLS Block 1 itself. At first glance, you might think this is a completely new rocket built from scratch for the Artemis program, but actually much of the core technology and hardware powering SLS Block 1 dates back nearly half a century. In many ways, it's a direct descendant of the Space Shuttle program, carefully modernized and scaled up. Standing about 98 meters tall, roughly the height of a 30-story building and weighing in at around 2.6 million kilograms, more than 5.7 million pounds when fully fueled, SLS is an absolute giant. Compared to the Space Shuttle stack, which stood just 56 meters tall and weighed roughly 2 million kilograms at launch, SLS is clearly a much bigger vehicle. And that's exactly the point. SLS was designed specifically for deep space missions. It completely abandons reusability. No winged orbiter, no parachutes on the boosters, no recovered hardware. Every kilogram of mass and every bit of energy is dedicated to one goal, pushing much heavier payloads much farther out all the way to the moon. At liftoff, SLS generates more than 8.8 million pounds of thrust, about 15% more than the legendary Saturn V. Though it's still only about half of what SpaceX's Super Heavy version 3 can produce with roughly 18.2 million pounds. But here's the interesting part. Most people don't immediately notice. The two giant solid rocket boosters, they're evolved directly from the Space Shuttle's SRBs. Same basic steel case design, same propellant chemistry, same manufacturing heritage going back to the 1970s. But each one now has 5 propellant segments instead of 4. That single extra segment makes them longer, heavier, and significantly more powerful, delivering over 75% of SLS's total liftoff thrust in just the first 2 minutes. The 4 RS-25 engines on the core stage, Those are upgraded versions of the exact same Space Shuttle main engines that flew from 1981 to 2011. NASA has modernized the controllers, improved some materials and manufacturing processes, but the fundamental engine design is still the one developed over 45 years ago. So, yes, SLS Block 1 is very much built on proven decades-old shuttle technology. All of this is connected to the Orion spacecraft, the crew capsule paired with its European-built service module, along with the necessary adapters and a set of small CubeSats carried along for scientific missions. So, was anything actually upgraded for Artemis 2? Yes, absolutely. Starting with the two solid rocket boosters, for Artemis 2, NASA made several subtle but meaningful changes. One internal insulation layer, known as the cap ply, was removed from inside the booster casing. That reduced weight slightly while improving reliability. Post-flight analysis from Artemis 1 showed that the simplified design performed better than expected, giving engineers confidence to streamline it further. The booster separation motors, 8 small motors on each booster that push them away from the core stage, were also adjusted. Their angle was rotated by about 15 degrees, increasing the clearance between the boosters and the core stage during separation. At the same time, their protective housing was switched from aluminum to steel, reducing the risk of debris striking the rocket. NASA even tweaked the timing of booster separation itself, moving it roughly 4 seconds earlier than on Artemis 1. That might sound trivial, but it improves overall efficiency and increases payload capability by about 726 kilograms. A very real gain for a mission like Artemis 2. Up on the upper stage, the Interim Cryogenic Propulsion Stage, or ICPS, also received a few targeted upgrades. Artemis 2 will fly with the RL-10C2 engine instead of the RL-10B2 used on Artemis 1, offering modest improvements in reliability and performance. The stage also gains GPS-based navigation to improve positioning accuracy in space, and the S-band antenna was relocated to ensure continuous communications with ground stations and the U.S. Space Force throughout the launch phase. The core stage itself remains largely unchanged, but it did receive a small update to the power distribution control unit. This addresses timing issues that showed up during the Artemis 1 countdown, helping make the launch preparation process smoother and more predictable. And finally, there's one upgrade that's unique to Artemis 2. Because it's a crewed mission, several adapters, including the launch vehicle stage adapter and the Orion stage adapter, now feature reflective optical targets. These aren't structural upgrades, they're training tools. After ICPS completes the translunar injection burn and separates, Orion will treat the departing ICPS as a target. The crew will practice approaching it, backing away, and observing it through windows and onboard cameras. It's a real-world test of proximity operations and manual rendezvous techniques, critical skills for future missions that will involve complex maneuvers and docking operations in lunar orbit. By this point, it's pretty clear that SLS is an extremely expensive and highly complex system. So, what happens when you put it side by side with SpaceX's Super Heavy? This is where the comparison gets really interesting, because despite aiming for the same ultimate goal, pushing humans deeper into space, these two launch systems could not be more different in how they're designed, built, and operated. Let's start with the numbers, because they tell the story better than anything else. The cost of a single SLS launch is estimated to fall somewhere between $2 and more than $4 billion per flight. That figure includes the Orion capsule and related program costs, based on reports from the NASA Inspector General and the Planetary Society, with early Artemis missions typically landing in the $2.5 to $4 billion range. Starship, on the other hand, is targeting something radically different. SpaceX's long-term goal is around $10 million per fully stacked launch, and once full reusability is achieved, that number could drop to just $2 to $3 million. That's not a marginal difference, that's a gap of hundreds of times in long-term marginal launch cost. Nowhere is this contrast clearer than in the engines. SLS flies with 4 RS-25 engines, each of which now costs roughly $100 to $146 million. That's well over $500 million just for the main engines on a single launch. Starship uses up to 39 Raptor engines. In its current Raptor 2 configuration, each engine costs about $1 million. And Raptor 3, expected to make its first flight next month, is targeting well under $500,000 per engine, potentially even closer to $250,000 with mass production. That brings the total engine cost for an entire Super Heavy stack down to somewhere between $10 and $40 million. But the real fundamental difference comes down to reusability. SLS is fully expendable. Everything the solid boosters, the core stage, the upper stage is used once and discarded. It's like driving a luxury supercar exactly one time and then setting it on fire. Starship is designed to be fully reusable. Both the Super Heavy booster and the Starship vehicle are meant to fly back, land, and be reflown. In that model, the marginal cost drops to fuel, maintenance, and labor, much closer to how commercial aircraft operate, flying thousands of missions without being rebuilt from scratch. Production philosophy only widens the gap. SLS is built slowly, with just 1 or 2 core stages produced every 1 to 2 years under cost-plus contracts, where NASA covers expenses and adds profit, leaving little incentive to aggressively cut costs or speed things up. SpaceX, by contrast, builds Starship almost entirely in-house at Starbase. The goal is high-rate, assembly line production, minimizing external suppliers, and iterating rapidly in hardware. Even the materials tell a story. SLS relies on expensive aluminum-lithium alloys for its tanks and extremely complex RS-25 engines that require extensive manual assembly. Starship, by contrast, uses thin stainless steel, just 4 millimeters thick, which is cheaper, easier to weld, and far better suited for mass production. Yes, it's heavier, but that penalty is more than offset by the sheer thrust and efficiency of the Raptor engines. And that difference shows up most clearly in payload capability. SLS Block 1 can deliver only about 27 to 30 tons to translunar injection, most of which is taken up by Orion and its European service module. Powered by Raptors, Starship is far more flexible, capable of flying directly to lunar orbit or integrating landing capability itself, as it will in its role as NASA's human landing system for Artemis 3. In the long run, Super Heavy and Starship have the potential to completely replace SLS for missions to lunar orbit and even beyond. The recent Wet Dress Rehearsal for Artemis, 2 conducted on February 2nd, initially looked like it was going according to plan, but in the end it was scrubbed midway through a familiar outcome for anyone who's been following the SLS program for years. Here's how it unfolded. Everything started smoothly around L48 hours from the evening of January 31st into the morning of February 1st. The SLS and Orion had already been looking great at Launch Complex 39B, and teams began powering up the core stage running electrical system checks and working through the early milestones exactly as planned. The closeout crew entered the White Room for final inspections, closed and sealed. Orion's hatch secured the launch abort system, and then cleared the pad, all standard procedure. Then came February 2, tanking day, the most critical phase of the WDR. This is when teams load cryogenic propellants, liquid hydrogen, and liquid oxygen into both the core stage and the ICPS upper stage. The process began with fast fill, and almost immediately trouble showed up. A liquid hydrogen leak was detected at the tail service mast umbilical interface, the massive umbilical that feeds propellant from the launch pad into the core stage. Hydrogen concentrations around the umbilical exceeded safety limits, forcing multiple pauses in LH2 flow while teams tried to troubleshoot the issue. NASA turned to the same playbook developed during Artemis 1 back in 2022, stopping the flow, checking seals, and adjusting pressures. After those interventions, tanking resumed. The core stage made it through. Fast fill transitioned into topping to keep the propellant at -423 degrees Fahrenheit, and then into replenish mode to maintain stable levels as hydrogen naturally boiled off. The ICPS upper stage tanking proceeded more smoothly. The hydrogen leak never fully disappeared, but it was judged to be within acceptable limits, and the team made the call to press ahead into terminal count. Terminal count began at around T-minus 10 minutes, but it didn't last long. At T-minus 5 minutes and 15 seconds, the countdown was abruptly halted. Once again, liquid hydrogen was leaking at the same tail service mast, umbilical location, and this time, concentrations climbed beyond safe thresholds. NASA chose not to take any risks. The wet dress rehearsal was officially terminated, and teams began fully draining the tanks to remove all propellant and eliminate the danger posed by the highly flammable hydrogen. NASA Administrator Jared Isaacman quickly posted an update after the scrub, and honestly, it only took the very first sentence to disappoint a lot of people. With the conclusion of the wet dress rehearsal today, we are moving off the February launch window and targeting March for the earliest possible launch of Artemis 2. And just like that, it was official. Artemis 2 is now delayed by more than a month, with the earliest launch opportunity opening no earlier than March 6th. But for many observers, that wasn't the real headline. What people are really asking is this: how can these hydrogen leak issues keep coming back again and again after decades of experience? And why were they still allowed to resurface on Artemis 2? Because this is clearly not new. During Artemis, one hydrogen leaks alone forced NASA to scrub the wet dress rehearsal 4 separate times. The vehicle had to be rolled back and forth between the launch pad and the VAB, repeatedly burning through money manpower and nearly 8 months of schedule. And long before SLS liquid hydrogen leaks were already a familiar nightmare during the space shuttle era. They plagued shuttle operations for decades, to the point where they became almost synonymous with launch delays at Kennedy Space Center. Veterans at KSC still talk about the infamous summer of hydrogen in 1990, a brutal period when the entire shuttle fleet was effectively stuck at the pad for months, grounded by stubborn, recurring hydrogen leaks that refused to go away. So, what's really behind these leaks? And why has this same problem continued to haunt NASA launch vehicles for decades, from shuttle to SLS, and now Artemis 2? In reality, liquid hydrogen leaks in launch systems like the Space Shuttle or NASA's SLS are not random accidents or simple assembly mistakes. They stem from the fundamental physics of liquid hydrogen itself, combined with engineering challenges that are almost unavoidable when dealing with such an extreme cryogenic propellant. Let's break this down layer by layer, the same way engineers do in technical reviews, or when we explain it to spaceflight enthusiasts. First, liquid hydrogen has to be stored at an incredibly low temperature, around minus 253 degrees Celsius, or minus 423 degrees Fahrenheit, just to remain in a liquid state. At these temperatures, every material involved, metals, seals, flanges, connectors, contracts significantly due to thermal contraction. Common rocket materials like stainless steel or aluminum alloys can shrink by several thousandths of their original dimensions. That may sound tiny, but it's more than enough to create microscopic gaps at interfaces that were perfectly tight at room temperature. Under normal conditions, those gaps wouldn't matter. With hydrogen, they absolutely do. That's because hydrogen is the smallest atom in the universe. Just like John Honeycutt, chair of the Artemis 2 mission management team, made clear during NASA's press conference yesterday.
When you're dealing with hydrogen, it's a small molecule, it's highly energetic, and we like it for that reason.
A hydrogen molecule is incredibly tiny, far smaller than helium or methane. This allows hydrogen to slip through pathways that other propellants simply can't: microscopic cracks, tiny voids and welds, and even in some cases directly through the crystal lattice of certain metals via a process known as permeation. When you add high pressure during fast fill operations, along with the extreme temperature difference between the super cold hydrogen and the surrounding hardware, the driving force pushing hydrogen outward becomes even stronger. The result is that hydrogen gas concentrations around critical interfaces like umbilicals or quick disconnect fittings can rise very quickly. Once those concentrations approach safety limits, typically around 4% by volume, operations have to be halted immediately to avoid the risk of ignition. That's exactly why leaks like these force scrubs so often, even when everything appears to be assembled correctly. The problem becomes even more severe at dynamic interfaces like the tail service mast, umbilical, or TSMU on SLS, and the ground umbilical carrier plate, the GU-CP on the Space Shuttle. These are quick disconnect systems designed to separate cleanly in the final seconds before liftoff. By definition, they cannot be clamped down like permanent bolted joints. They must release instantly without sticking, binding, or tearing hardware apart. That puts enormous demands on the seals typically made from materials like Teflon, indium, or other cryogenic-rated compounds. These seals have to survive repeated hot-cold cycles, high pressures, and vibration, all while maintaining a near-perfect seal against liquid hydrogen. But when temperatures plunge rapidly during chill-down, seals can contract unevenly. Flanges can shift slightly due to pipe routing loads or torque imbalance. And when that happens, seals can deform, shift out of position, get crushed, or open up microscopic gaps. During Artemis 1 in 2022, the infamous leak at the 8-inch quick disconnect was traced back to a valve opening out of sequence during chill down, causing overpressurization that damaged a soft seal. On the shuttle, recurring GUCP leaks between 2009 and 2010 were often linked to worn seals or cracking at the inner tank flange under cryogenic stress. So, why does this keep happening even after everything NASA learned from shuttle? Because SLS reuses heritage hardware, upgraded RS-25 engines, and design philosophies carried over from the external tank, but at a much larger scale. The SLS liquid hydrogen tank is the largest ever built. Hydrogen flow rates are higher, pressures are higher. Thermal shock during fueling is more intense. Everything expands and contracts more, and does so more violently. And every new integration introduces variability. Even with familiar hardware, small differences matter. How bolts are torqued, microscopic debris on a sealing surface, millimeter-level alignment errors, or vibrations transmitted through the mobile launcher. SLS is in many ways rediscovering those same hazards. Because liquid hydrogen is unforgiving, it doesn't tolerate tiny mistakes. And when you push it through massive complex ground interfaces, it will find the weakest point every single time. Now when you put liquid hydrogen on SLS side by side with liquid methane on SpaceX's Starship, you start to see one of the most fascinating contrasts in modern rocket development. This isn't just about performance numbers anymore. It's a clear reflection of two fundamentally different philosophies about how humanity should conquer space. Let's start with methane CH4. It's a much larger molecule compared to hydrogen's H2. That alone makes a huge difference. Methane is far less likely to slip through microscopic gaps, which dramatically reduces permeation through materials and natural leakage. Its boiling point is also much higher, about minus 162 degrees Celsius, nearly twice as warm as liquid hydrogen at minus 253 degrees. That means methane tanks don't need extreme insulation. Boil-off happens much more slowly, and pipes, valves, and connectors experience far less violent thermal shock during fueling. Seals are easier to design, less prone to uneven contraction, and from an engineering standpoint, the entire system is simply more forgiving, fewer leaks, fewer scrubs, and far less pad-side troubleshooting. In pure performance terms, methane does lose to hydrogen, at least on paper. SpaceX's Raptor engines deliver a specific impulse of roughly 330 to 350 seconds at sea level and around 375 to 380 seconds in vacuum for the latest vacuum-optimized variants. By comparison, the RS-25 engines on SLS, running liquid hydrogen and liquid oxygen, achieve about 366 seconds at sea level and an impressive 452 seconds in vacuum. That's a massive gap. Hydrogen offers the highest efficiency you can realistically get from conventional cryogenic propellants. With the same propellant mass, you get more delta V, more payload, or more range. That's why hydrogen was long considered the king of upper stages in deep space propulsion. So, why didn't SpaceX choose hydrogen, even though they absolutely could have? The answer lies in real-world trade-offs and long-term vision. Methane is far denser than hydrogen, about 0.42 grams per cubic centimeter versus just 0.07 for liquid hydrogen. That means much smaller tanks, shorter plumbing, lighter structures, and a more compact overall vehicle. For Starship, that's critical. This is a fully reusable super heavy lift system designed to fly, often refuel in orbit, and eventually operate far from Earth. During the recent visit by officials from the U.S. Department of Defense and the Secretary of War to Starbase SpaceX, appears to have deliberately revealed a very important detail. Right there at Starbase's brand new Raptor, 3 engines had already been delivered, and they weren't hidden away. Instead, SpaceX placed them directly on the stage as part of the presentation, almost like a deliberate statement. The engines were fitted with blue lead lighting, giving them a mysterious yet powerful look. And that choice of color wasn't accidental. Blue is the signature color of the Raptor's methane flame, a subtle but very intentional visual cue. What's even more interesting is the number. There were 5 Raptor 3 engines on display, and that strongly suggests SpaceX already has more on site, preparing for Ship 39 and Booster 19. If you break down the numbers, the scale becomes clear. Booster 19 alone requires 33 engines. Ship 39 will need 6 more 3 sea-level Raptors and 3 vacuum variants. On top of that, SpaceX would realistically need another 10 or so engines as spares. Why? Because during static fire testing, it's not uncommon for a few engines to show issues and need replacement. And considering this is the very first production batch of Raptor 3, the likelihood of early failures is relatively high. That's simply how development works. These initial engines are meant to be tested hard pushed to their limits and refined in the later production runs. And that brings us to a debate that recently reignited across the spaceflight community. Is Raptor 3 actually the most powerful rocket engine in the world? One commenter pointed out that a 350 bar chamber pressure isn't just high, it's a physical record, and Elon Musk responded directly. He revealed that SpaceX has already pushed the engine beyond 350 bar during testing, but not yet to a level that's safe and stable enough for sustained operation. In other words, they've reached it, but they can't reliably run there without risking hardware damage. Still, Elon sounded optimistic. With further refinements, he believes SpaceX can turn above 350 bar pressure into a normal operating condition. And he emphasized an important benchmark: anything above 270 bar already qualifies as a world record-placing Raptor 3 firmly ahead of every other rocket engine on the planet. And that claim is not speculative. It's grounded in decades of engine history. Before Raptor, the long-standing record belonged to Russia's RD-180 with a chamber pressure of around 257 bar, or up to 267 bar, according to some sources. That record held for decades, which is precisely why the United States chose to purchase the RD-180 for use on the Atlas V rocket. Over more than 20 years, Russia supplied roughly 122 RD-180 engines to the U.S., but that era is now firmly in the past. In 2019, Raptor 1 reached approximately 268 to 270 bar, effectively matching, and in some cases surpassing the RD-180 benchmark. Raptor 2 then went further, operating stably at around 300 bar, and now Raptor 3 has pushed chamber pressure into the 330 to 350 bar range during testing. With that progression, SpaceX has effectively taken sole possession of the global lead in combustion chamber pressure, a critical metric that directly drives engine performance, thrust, density, and reusability. Now, just to clarify, a bar is a unit of pressure roughly equivalent to 1 Earth atmosphere at sea level. In rocket engines, it refers specifically to the pressure inside the main combustion chamber, where liquid methane and liquid oxygen are burned under extreme heat and forced to generate thrust. Reaching pressures this high isn't just a technical statistic. It's what turns Raptor 3 into a true performance monster. Higher chamber pressure means denser exhaust flow, more thrust, better fuel efficiency, and greater payload capability. Exactly what Starship needs to reach, orbit the Moon, and eventually Mars. For comparison, engines like Merlin and even Raptor 2 typically operated around 230 to 250 bar. Raptor 3 with a 330 bar nominal operating pressure represents a massive leap forward. It directly enables faster reuse, lower costs, and higher overall reliability. And Elon made it clear, this isn't the ceiling. As he put it, we should be able to achieve operating pressures higher than 350 bar, not just briefly touching that number, but sustaining it. Once challenges like thermal control, flow stability, and material strength are fully solved, preventing combustion chamber, rupture, or turbo pump failure. So, why does SpaceX deliberately push the engine beyond its rated limits? Because overtesting isn't reckless, it's essential in aerospace development. Engineers have to break limits to discover weaknesses and reinforce strengths. Think of Raptor 3 as a living machine designed to withstand pressures equivalent to hundreds of times the force found at the bottom of Earth's deepest oceans. Superheated plasma flows through it without traditional heat shielding. Minor leaks are intentionally burned off instead of sealed, reducing mass and increasing robustness. By testing far beyond nominal limits, SpaceX gathers critical data on vibration, extreme temperatures, and material fatigue. That data is what allows the engine not just to survive real flights, but to operate smoothly through hundreds of reuse cycles. This matters enormously for Elon Musk's multi-planet ambitions. A more powerful engine means fewer refueling launches, shorter mission timelines, and lower risk for crewed missions. And on a 6-month journey to Mars, engines must endure the harsh thermal environment of deep space without failure. Without pushing this hard, we'd remain stuck at old safety margins. But it's precisely this pursuit of seemingly crazy numbers that has transformed Raptor 3 from a paper concept into a symbol of real progress, even if at first glance its minimalist design makes it look unfinished to those unfamiliar with SpaceX's philosophy. The striking contrast between Raptor 3's almost shockingly minimalist appearance and its raw destructive power is no accident. It's the direct result of SpaceX fully embracing its internal design philosophy, known as the algorithm, a ruthless process aimed at eliminating anything that isn't absolutely necessary. When experts in the rocket propulsion community first look at Raptor 3, many are genuinely surprised by how clean it appears. The engine is smooth, almost sculpted with none of the tangled plumbing external lines or complex wiring bundles seen on previous generations. The secret lies in a radical architectural shift. SpaceX has integrated nearly all plumbing sensors and auxiliary systems directly into the engine's primary structure, routing them through regenerative cooling channels. This so-called pipeless architecture represents a major leap forward. By embedding these systems internally, the engine protects itself from extreme heat without relying on heavy external heat shields. The result is dramatic, roughly 1 metric tons of mass saved per engine cluster and associated hardware on the vehicle. What looks like simplicity is actually sophistication at a higher level. Fewer parts, fewer joints, fewer flanges, and far fewer potential failure points. Just as importantly, this design is optimized for high-rate mass production, enabling SpaceX to manufacture engines at unprecedented speed, potentially dozens per day. But beneath that clean exterior is a mechanical monster operating far beyond conventional limits. Raptor 3 derives its extraordinary performance from a full-flow stage combustion cycle, a long-sought holy grail of rocket engine design that no organization had successfully deployed in operational service before SpaceX. In this system, both liquid methane and liquid oxygen are fully gasified before entering the main combustion chamber, maximizing efficiency and enabling chamber pressures that were once thought impractical. Raptor 3 operates at a nominal chamber pressure of around 330 bar, and during aggressive testing has already exceeded 350 bar. This extreme pressure is the key to generating approximately 280 tons of thrust, with a clear path toward 300 tons, all within a far more compact engine than traditional designs. Surviving this internal environment effectively, a controlled mechanical hell requires materials at the edge of what's possible. SpaceX relies on proprietary superalloys such as SX500 combined with advanced metal 3D printing, allowing the creation of highly complex structures with exceptional thermal conductivity and the strength to withstand tens of thousands of psi without deformation. The result of combining extreme simplicity with extreme performance is a remarkable metric, a thrust-to-weight ratio of roughly 184, surpassing even the legendary Merlin 1D. Raptor 3 isn't just more powerful, it's designed for rapid reuse targeting 50 or more flights with minimal refurbishment. As Elon Musk has repeatedly emphasized, simplification isn't about aesthetics. It's about transforming rocket engines from expensive handcrafted artifacts into true industrial products, engines that can be mass-produced for under $500,000, and eventually as low as $250,000. Turning that philosophy into reality would be impossible without a radical shift in manufacturing, and this is where SpaceX's deep partnership with Velo 3D becomes critical. SpaceX has worked closely with the Velo 3D, a leader in advanced metal additive manufacturing, to produce some of the most complex components of the Raptor engine, particularly for Raptor 3 and later variants. To support this effort, SpaceX acquired more than 22 Velo 3D sapphire metal 3D printers based on laser powder bed fusion technology. In 2024, the collaboration went even further. The two companies signed an $8 million technology licensing agreement, $5 million for the license itself, and $3 million for engineering support, granting SpaceX the right to use, modify, and further develop this manufacturing technology internally for rocket engine production. This capability fundamentally changes how engines like Raptor 3 are built. Advanced metal 3D printing allows SpaceX to consolidate dozens of separate parts into single monolithic structures, embed highly complex internal cooling channels, reduce mass, and eliminate the need for external heat shields and auxiliary fire suppression systems. Just as importantly, it dramatically accelerates design iteration while improving reliability. Elon Musk has openly acknowledged this advantage, stating on X, "It is not widely understood that SpaceX has the most advanced 3D metal printing technology in the world, and it's precisely this combination of full internal control over additive manufacturing and an engine designed around it that enables Raptor 3's astonishing level of simplification, higher performance, and true mass production readiness for Starship." By late January 2026, the International Space Station had entered a very unusual and very challenging phase. For a brief period, the ISS was operating with just 3 crew members, what insiders call a true skeleton crew. These 3 astronauts were part of Expedition 74. The team included NASA astronaut Chris Williams, serving as a flight engineer, alongside 2 Roscosmos cosmonauts, Sergei Kudzverchkov, who was acting as the commander of the entire ISS, and Sergei Mikhaev, also serving as a flight engineer. All 3 arrived at the station aboard Soyuz MS-28, which launched from the Baikonur Cosmodrome on November 27, 2025. By this point, they had already been living and working in orbit for more than 2 months. Now, operating the ISS with only 3 people is a massive strain. Under normal conditions, the station is designed to be run by a crew of 7. With less than half that number on board, the workload becomes intense very quickly. Daily operations were reduced to the absolute essentials, keeping critical life support systems running, performing only the most basic scientific experiments, monitoring the station's automated systems, and staying ready to respond to any emergency at a moment's notice. Thanks to the ISS's highly redundant design and advanced automation, the station remained stable and safe. But many labor-intensive or complex activities had to be scaled back or postponed entirely. Larger scientific experiments, deep maintenance work, and especially spacewalks, whether to repair areas damaged by orbital debris or to deploy and service solar panels, were delayed to avoid pushing the crew beyond safe limits. Soyuz MS-28 is currently scheduled to depart the station and return to Earth in late July 2026. That means this 3-person crew has roughly 4 months left to complete their mission before finally heading home. The situation became this tense because of an unexpected event in mid-January 2026. NASA was forced to make a rare and difficult call, the Crew 11 mission flying aboard SpaceX's Crew Dragon, with 4 astronauts had to return to Earth earlier than planned after one crew member developed a serious medical issue. Crew 11 included NASA astronauts Zena Cardman and Mike Finka Jaksa, astronaut Kimia Yui, and Roscosmos cosmonaut Oleg Platonov. The spacecraft undocked from the ISS on January 14th and performed a safe splashdown off the coast of California on the morning of January 15th. This marked a historic first. In more than 25 consecutive years of continuous human presence on the ISS, this was the first time NASA had carried out a controlled medical evacuation from the station. According to official statements, the situation was described as stable, not an immediate life-threatening emergency. Still, NASA chose to bring all 4 crew members back together, prioritizing a full medical evaluation on the ground, rather than leaving part of the crew in orbit. However, that decision immediately raised eyebrows. Only 1 astronaut was reported to have medical issues, not all 4. And during post-landing interviews, every member of Crew 11 appeared visibly healthy, fueling speculation across spaceflight communities. Some online discussions even floated unverified theories, such as the possibility that Zena Cardman, the only woman on the Crew 11 team, might have been pregnant. But it's important to stress these were purely rumors. Astronauts undergo extremely rigorous medical screenings before launch, and NASA has never confirmed any such scenario. What is clear, though, is that Crew 11's early departure dramatically reshaped the crew balance on the ISS, leaving the station operating with a minimal skeleton crew and pushing NASA into a race against time to stabilize the situation. To close that gap on the ISS as quickly as possible, NASA and its international partners moved fast, accelerating preparations for Crew 12, the next four-person team, scheduled to fly aboard SpaceX's Crew Dragon. Their training timeline was significantly compressed. The crew went through full mission simulations covering everything from emergency scenarios and ISS docking procedures to system failure management and even preparations for potential EVAS if needed. At SpaceX's facilities in Hawthorne, California, the crew focused heavily on Dragon spacecraft systems, the Falcon 9 launch vehicle station, robotics, space medicine, and multinational crew coordination. Each astronaut also received specialized training tailored to their specific responsibilities, scientific experiments, and ISS maintenance tasks. Crew 12 is led by NASA astronaut Jessica Meir as commander with Jack Hathaway serving as pilot, ESA astronaut Sophie Audinot, and Roscosmos cosmonaut Andrei Fedyaev round out the team as mission specialists. Because Crew Dragon is a complex commercial spacecraft, every crew member must achieve 100% flight readiness certification before launch. Any delay at this stage would risk extending the skeleton crew period on the ISS, something that could have serious consequences for both safety and ongoing research. Fortunately, things appear to be moving in the right direction. NASA and SpaceX have confirmed that Crew 12 completed a major phase of training in California during the final week of January. The Falcon 9 is currently targeted to launch Crew Dragon in February 2026, with a no earlier than date of February 15th. While an exact launch date has not yet been locked in pending final readiness reviews, weather conditions, and technical checks, the current situation has clearly pushed all teams to move as quickly as possible. If everything lines up, the launch could happen in mid-February or even a few days earlier. Once Crew 12 arrives at the station, the ISS crew will return to 7 astronauts, total 3 from Soyuz, MS, 28, and 4 from Crew 12. Expedition 75 will officially begin, and station operations can ramp back up to normal levels. The new crew balance of roughly 3 Roscosmos cosmonauts and 4 NASA/ESA astronauts will allow workloads to be distributed more evenly, enabling a full return to scientific research, maintenance activities, and long-term planning. In short, while the current 3-person skeleton crew has placed significant pressure on ISS operations, the situation remains well under control thanks to a rapid coordinated response from NASA Roscosmos and SpaceX. With Crew 12 set to launch in February, this gap appears to be temporary, and the ISS is on track to resume full operations, continuing its long-term mission in low Earth orbit. But don't celebrate just yet. The domino effect triggered by Crew 11's early return hasn't stopped, and it could resurface again in the second half of 2026. The core of the problem lies on the Roscosmos side. Launch site 31/6 at Baikonur, currently the only pad certified to launch crewed Soyuz spacecraft and Progress cargo vehicles to the ISS, suffered serious structural damage shortly after the successful launch of Soyuz MS-28 on November 27, 2025. In response, Roscosmos deployed more than 130 personnel working in 2 continuous shifts from 8 a.m. until midnight, along with 18 heavy trucks delivering replacement components to Baikonur. According to Dmitry Baranov, Deputy Director General of Roscosmos, the agency is confident repairs will be completed by the end of February 2026, or what he described as the end of winter 2026. Some independent experts, including space historian Anatoly Zak, have warned that repairs of this scale could take up to 2 years. However, Roscosmos has prioritized the effort and claims key hardware is already available, allowing them to target a much earlier return to service. As of now, more than 2 months have passed since the incident, with no public indication that the repair timeline has slipped, but also no signs it has been completed ahead of schedule. The immediate consequence is that Soyuz MS-29, scheduled to launch on July 14, 2026, is entirely dependent on that same launch pad. MS-29 is slated to carry Pyotr Dubrov and Anna Kikina of Roscosmos, alongside NASA astronaut Anil Menon. If repairs finish on time, MS-29 can still launch as planned, allowing for a brief overlap with Crew 12, which is expected to return around August or September 2026. That overlap is critical for maintaining operational continuity on the ISS. But if repairs slip by even a few weeks, the consequences escalate quickly. When Soyuz MS-28 returns to Earth in late July 2026, the ISS could once again be left with a reduced crew of just 4 astronauts, all from Crew 12. 4 people is certainly better than the current 3, but the workload would still be heavy. Scientific output, especially on the Russian segment, would likely be scaled back and overall safety margins would shrink. In the event of a major anomaly, more hands are simply better when multiple systems need to be managed at once. At that point, the pressure shifts squarely onto NASA and SpaceX. Since December 2025, Roscosmos has been unable to launch any Progress resupply missions, with flights such as Progress MS-33 delayed. As a result, Cargo Dragon has been carrying the bulk of the load food, scientific payloads, oxygen, and replacement hardware. Crew rotation has also become entirely dependent on Crew Dragon during this period. The seat swap agreement between NASA and Roscosmos remains in effect through 2027, meaning Russian cosmonauts continue to fly aboard Dragon, such as Andrei Fedyaev on Crew 12, while NASA astronauts still fly on Soyuz, like Chris Williams aboard MS-28. But if launch delays persist, Roscosmos may have little choice but to purchase additional commercial services from SpaceX, whether individual seats or dedicated cargo flights. There's a certain irony here. During the Dmitry Rogozin era, Russian officials openly mocked Crew Dragon, calling it a broomstick or a trampoline, while charging NASA steep prices for Soyuz seats between 2011 and 2020. Now, Russia may find itself paying to ensure a continuous cosmonaut presence on the Zeus SS, a requirement under international agreements to maintain safety and uninterrupted station operations. And the implications go beyond the near term. The ISS is a critical testbed for future programs like Artemis, the Gateway Lunar Station, and eventual human missions to Mars. Research into radiation exposure, microgravity effects, and long-duration life support systems all depend on consistent crew presence. If skeleton crew operations drag on, scientific data streams are disrupted, indirectly impacting NASA's long-term exploration roadmap. That's why NASA and SpaceX are handling the situation with remarkable finesse, largely thanks to the flexibility and speed of the commercial crew program. Right now, the biggest bright spot is Cargo Dragon, which has effectively been carrying the load for the supplies Russia hasn't been able to launch, largely because Baikonur's Site 31/6 remains under repair, with completion still targeted for late February 2026. To compensate, NASA has pulled several CRS missions forward. CRS-34 has been moved up to May 2026 instead of June, while CRS-35 is now planned for August 2026 rather than November. Falcon 9 has long been regarded as one of the most reliable rockets ever built. As of the time you're watching this video, SpaceX has carried out nearly 610 launches, with an overall mission success rate of about 99.5% across earlier Falcon 9 variants. The current Block 5 version performs even better, pushing close to a 99.8% success rate across hundreds of consecutive flights. No other rocket on Earth flies at this kind of cadence almost weekly, sometimes just days apart, while maintaining that level of consistency and reliability. But even the most dependable machines can reveal a weak point. And that's exactly what happened just 2 days ago, on February 2nd, 2026. A Falcon 9 lifted off from Vandenberg Space Force Base in California at 10:47 a.m. Eastern Time, carrying 25 Starlink V, 2 mini-optimized satellites. For most of the mission, everything looked like a textbook. The first stage separated and landed on the drone ship as usual. The upper stage executed 2 smooth burns of its Merlin vacuum engine, delivered the payload to the intended low Earth orbit, and deployed the satellites right on schedule just 62 minutes after liftoff. The payload was safe. By most definitions, the mission itself was a success. But the real problem surfaced roughly 9 hours later as the upper stage prepared for its final task, the deorbit burn. This burn is designed to send the stage back into Earth's atmosphere in a controlled manner, targeting a remote region of the South Pacific to prevent long-term debris from being left in orbit. However, as the mission entered its final phase, something went wrong. The upper stage attempted to restart its Merlin vacuum engine for the final deorbit burn, and the engine failed to ignite. The burn never happened. As a result, the stage was left stranded in a very low elliptical orbit, with a perigee of roughly 110 kilometers and an apogee of about 241 kilometers. At such a low perigee, the stage repeatedly passes through the denser upper layers of Earth's atmosphere, on every orbit experiencing significant drag and rapidly losing energy and altitude. The outcome is inevitable. The stage will re-enter the atmosphere naturally within just a few days, likely somewhere between 2 and 5 days, depending on atmospheric conditions and solar activity. Fortunately, SpaceX's safety systems performed exactly as designed. The upper stage was fully passivated, all remaining liquid oxygen and RP-1 propellant were vented, and the onboard batteries were discharged, eliminating the risk of an explosion or the creation of hazardous secondary debris. As a result, there is no immediate danger to people on the ground, no credible risk of debris impacting populated areas, and all 25 Starlink satellites were successfully deployed into their intended orbit. Still, this remains a notable anomaly. Failing to execute a controlled deorbit means the stage is coming down naturally rather than being precisely guided into the ocean. And in the context of SpaceX's extremely high launch cadence, repeated incidents like this could increase long-term concerns around orbital debris management and collision risk. Just hours after the anomaly was confirmed, SpaceX released an official statement on its X account, updating the community on what had happened. In the post, SpaceX acknowledged that the upper stage experienced an off-nominal condition while preparing for its deorbit burn. At the same time, the company emphasized that all other aspects of the mission performed well, an important distinction. And this wasn't the first time Falcon 9 has run into trouble with its upper stage, especially during the deorbit phase. We've seen a pattern emerge over the past few years. Back in July 2024, a Merlin vacuum engine failed to restart due to a liquid oxygen leak caused by a crack in a pressure sensor line. That incident left both the upper stage and an entire batch of Starlink satellites in an orbit that was too low to sustain, resulting in a complete mission loss. It was one of the very few full mission failures Falcon 9 has suffered since 2016. Then in September 2024, during the crewed Crew 9 mission, the upper stage again encountered a deorbit issue re-entering outside the planned target zone in the South Pacific. SpaceX voluntarily paused Falcon 9 launches for roughly 2 weeks, while the FAA reviewed the incident. And in February 2025, history repeated itself. Another upper stage deorbit failure, this time linked to a propellant leak, led to an uncontrolled re-entry over Europe with debris landing in Poland. Fortunately, no injuries or damage were reported. Across these incidents, the underlying causes have often traced back to familiar themes: liquid oxygen leaks, sensor faults, or difficulties restarting the Merlin vacuum engine after a long coast phase. Because of that history, SpaceX made a decisive call. The company temporarily grounded the entire Falcon 9 fleet across Florida, Texas, and California, halting all launches until engineering teams could fully analyze the telemetry data, identify the root cause, and implement corrective actions. A satellite launch originally scheduled from Florida on February 3rd has already slipped to February 5th, and other missions remain on hold. This is a cautious move, especially with Crew 12 looming just days away. The mission set to launch on February 11th will carry 4 astronauts to the International Space Station. NASA is watching the situation closely, and if the grounding drags on the crew rotation schedule aboard the ISS could be seriously disrupted, because right now the United States relies almost entirely on SpaceX's Crew Dragon to get astronauts to orbit. Still, there's no need to panic. This is actually where SpaceX tends to perform at its best. The company is well known for its extremely fast internal investigations. After similar incidents in the past, SpaceX has typically returned to flight within just 1 to 3 weeks, not months, as is often the case with traditional launch programs. Those recoveries usually involved relatively minor hardware tweaks, tighter inspection procedures, and a rapid green light from the FAA. When it comes to Crew 12, human safety is the top priority. SpaceX will not take any risks if there's even a hint of uncertainty. That said, there are early signs that the situation may be stabilizing faster than many expected. Less than half a day after posting its initial Falcon 9 anomaly update, SpaceX shared another post. Dragon arrives at the hangar at Pad 40, ahead of the upcoming Crew 12 launch to the space station. Alongside the post were images of the Crew Dragon capsule and its trunk looking pristine, bright white, and almost factory fresh, as if the vehicle had just rolled off the production line. As of now, Crew 12 is still scheduled to launch earlier than February 11th, 2026 at 6 a.m. Eastern Time. This will be SpaceX's 13th crewed Crew Dragon mission under NASA's Commercial Crew Program. The flight will carry 4 astronauts to the International Space Station, NASA's Jessica Meir as commander and Jack Hathaway as pilot, joined by ESA, astronaut Sophie Adenauer, and Roscosmos cosmonaut Andrei Fedyaev. They will relieve Expedition 74 and spend roughly 6 months aboard the ISS. The crew has already entered official quarantine, beginning their final physical and psychological preparations for the mission. With more than a week still remaining until launch, there is sufficient time for SpaceX to complete its root cause analysis, implement any required fixes, and provide updated guidance. NASA officials are watching closely. In a recent briefing, Amit Kshatriya confirmed that preparations for Crew 12 are entirely dependent on the outcome of SpaceX's investigation and the corrective actions that follow. Even so, this is happening at a moment when NASA is relying on SpaceX more than ever to maintain a continuous human presence aboard the International Space Station. It's worth remembering the broader context. Since 2020, when NASA's Commercial Crew Program officially came online, SpaceX's Crew Dragon has become the only reliable vehicle capable of flying U.S. and partner astronauts to the ISS on a regular basis. Boeing's Starliner, the intended competitor, continues to struggle with a long list of technical problems, from helium leaks and propulsion issues to unusually prolonged uncrewed test flights, preventing NASA from certifying it for routine crewed missions. As a result, the entire U.S. crew rotation system aboard the ISS now depends almost entirely on SpaceX. Every few months, a Crew Dragon launches with 4 astronauts relieving the previous crew and ensuring the station never goes unstaffed, a critical requirement for keeping scientific experiments and daily operations running. Right now, with Expedition 74 nearing the end of its mission, Crew 12 sits right at the center of that delicate rotation. All that's left is to wait a few more days as official updates from Hawthorne and Houston roll in to see whether Crew 12 will indeed lift off on February 11th. In the space industry, it's moments like these, filled with tension, uncertainty, and high stakes, that often make the story most compelling. But while all eyes remain on Falcon 9, there's another development worth talking about. And now, to change gears after all, the Falcon 9 drama. Let's turn to a piece of news that really caught attention, announced by Vast just yesterday on February 3rd, 2026. Vast, the company quietly nurturing ambitions to one day replace the ISS with commercial space stations, posted an update on X along with a genuinely striking video. Their Haven demo spacecraft has successfully completed its first perigee lowering maneuver in orbit. This is not a minor milestone. It's a critical proof point showing that Vast can actively and deliberately bring a spacecraft back into Earth's atmosphere in a safe, controlled way, instead of letting it drift until it becomes yet another piece of space junk, like so many satellites before it. So, what exactly happened? Haven Demo fired its orbital maneuvering system for roughly 14 continuous minutes, a fairly long burn for a compact demo vehicle like this. The result was a perigee lowered to about 170 kilometers, effectively pushing the spacecraft deeper into the denser layers of Earth's atmosphere, where natural drag will take over and bring it down to burn up completely within the next few days. The video that came with the post is honestly goosebump-inducing. From an onboard camera, Earth appears as a shimmering blue gem, with the thin curved edge of the atmosphere glowing in the distance. The golden solar panels gently vibrate with the rhythm of the engine burn. You can clearly make out the propellant lines, the small thrusters, and a host of engineering details, all minimalist, all purposeful, all remarkably elegant. And that shot isn't just beautiful. It sends a very clear message. Vast isn't just building technology to reach orbit, but to leave orbit cleanly and responsibly, fully aligned with modern space debris mitigation rules. And the contrast is hard to miss, especially when just 24 hours earlier, Falcon 9's upper stage ran into trouble in almost the exact opposite direction. Elon Musk just sent the space community into overdrive after casually posting on X Starship launch in 6 weeks. A short sentence, but one with massive implications shared alongside a dramatic image of Starship staging against the night sky. What makes this so striking is how quickly the timeline has solidified. Just a few months ago, we were still estimating launch windows based on vehicle progress and pad readiness. Now, SpaceX's founder himself has effectively locked in a target. If Musk's timeline holds Starship Flight 12 is shaping up for early March 2026. With it now, late January, that 6-week window means teams at Starbase are in full sprint mode. Cryogenic testing static fires, final integration, and last-minute checkouts are all lining up fast, as Booster 19 and Ship 39, the first Block 3 Starship pair, move toward the launch pad. In other words, this isn't speculation anymore. Starship Flight 12 is officially on the clock. At Launch Pad 2 at Starbase, SpaceX has just carried out a relatively rare but extremely important test involving the Detonation Suppression System, or DSS. This system is one of the most critical layers of protection integrated directly into the orbital launch mount at Pad 2, designed to shield the infrastructure from the sheer destructive power of Super Heavy's 33 Raptor engines. When those engines ignite simultaneously, they generate an acoustic storm that can reach 160 to 170 decibels, combined with plasma flames at thousands of degrees and truly enormous thrust. If left unchecked, these forces can warp steel fracture concrete or even trigger secondary detonations caused by trapped methane and liquid oxygen beneath the booster. The DSS is SpaceX's solution to this problem. It works by blasting an enormous volume of clean water, around 3,000 gallons upward, through nozzles embedded beneath the launch mount, starting just before ignition and continuing through the critical early phase of engine startup. This water absorbs acoustic energy, dramatically reducing shock waves, while also cooling the pad surface, deflecting exhaust flames outward and preventing extreme heat from damaging the structure. This design is a direct response to the hard lesson learned during Flight 1 in 2023, when the original pad suffered catastrophic damage due to the absence of a fully capable deluge system, leaving a massive crater and forcing a near-total rebuild. People sometimes use DSS and water deluge system interchangeably, but at Starbase there is a subtle distinction. DSS typically refers to the upward-firing launch mount integrated system that creates what is essentially a violent reverse rain beneath the booster. The broader water deluge system includes additional water delivery paths from multiple directions designed to protect the pad as a whole. SpaceX usually tests the DSS either in standalone runs or during wet dress rehearsals, where high-pressure water flow is used to verify activation timing, flow rate, and full engine area coverage. What we're seeing here, water erupting skyward in a chaotic, almost explosive spray, is exactly that. These tests can last anywhere from a few seconds to several minutes and are often paired with pipe flushing to clear debris check for leaks and validate system integrity. All of this is happening as SpaceX prepares for Starship Flight 12, also known as IFT-12, which is expected to be the first flight of the Block 3 or Version 3 Starship system, featuring Booster 19 and Ship 39. DSS and deluge testing at Pad 2 has clearly ramped up with one primary goal: ensuring the pad can safely handle higher loads, support a faster launch cadence, and accommodate the upgrades introduced with Block 3, most notably the more powerful Raptor 3 engines, lighter vehicle structures, and improved thermal resilience. The sequence we're seeing now, waterline flushing DSS tests, followed by full deluge runs, marks the final commissioning phase for Pad 2. It strongly suggests that major structural, electrical, and data systems are already in place, and that SpaceX is now focused on validating pad protection at maximum operating pressure. If these tests are successful, the next steps would be rolling Booster 19 to the pad, beginning static fire campaigns and moving toward full engine testing. The broader significance of these tests goes far beyond a single flight. This is about durability and rapid reuse. If Starship is going to fly frequently dozens or eventually hundreds of times per year, the launch pad itself cannot be treated as a disposable asset. A properly functioning DSS allows Pad 2 and later an upgraded Pad 1 to survive repeated launches without major repairs. That reliability is essential for Block 3's more ambitious goals, including orbital refueling demonstrations and large-scale Starlink deployments. If everything checks out, SpaceX will have another major piece in place to accelerate operations at Starbase, bringing it one step closer to becoming not just a launch site, but a real Mars gate. In another fascinating development on January 25th, 2026, during the launch of Starlink Group 17-20 from SLC-4E at Vandenberg Space Force Base in California, SpaceX pulled off a move that caught many observers by surprise and impressed a lot of people. For this mission, SpaceX attached several black, hexagonal, heat shield tiles, identical in appearance to the tiles used on Starship's belly, directly onto the outer surface of a Falcon 9 payload fairing. These tiles did not cover the entire fairing. Instead, they were installed in small, isolated clusters mounted on top of an underlayment layer designed to improve adhesion. The tiles were clearly visible on pad cameras and in SpaceX's official live stream, and crucially, they remained firmly in place through ascent and fairing, jettison indicating they survived vibration, acceleration, and the launch environment without detaching. The spaceflight community immediately lit up on X, with multiple independent observers confirming that this appears to be the first time SpaceX has flown Starship heat shield tiles on another launch vehicle, specifically Falcon 9. While there has been no official statement from Elon Musk or SpaceX, the test was far too visible and deliberate to dismiss. Many called it a genius move because it leverages Falcon 9's extremely high launch cadence to collect real-world data without having to wait for Starship, which only flies every few months and is still preparing for Flight 12. Importantly, this was almost certainly not about protecting the Falcon 9, fairing from re-entry heating. Falcon 9 fairings re-enter at roughly Mach 4 to Mach 5, experiencing surface temperatures far lower than Starship, which slams into the atmosphere at Mach 25 and endures plasma heating reaching thousands of degrees Celsius. The current fairing design is already optimized for reuse dozens of times with lightweight coatings and shows no serious thermal or erosion issues. Adding heavy, expensive Starship tiles purely for fairing protection would make little sense. Instead, this looks like a smart, low-cost flight test for Starship's next-generation heat shield, likely tied to Block 3 or future upgrades. The tiles flown here could represent an updated design, new ceramic material, mixes for higher durability, and lower mass, improved resistance to plasma erosion, enhanced surface coatings to reduce ablation or discoloration, or most critically, new mounting and attachment methods. Tile retention has been a recurring challenge on previous Starship flights, so SpaceX may be testing revised adhesives, mechanical pins, or hybrid mounting systems. By placing the tiles in isolated clusters rather than continuous coverage, SpaceX may also be simulating gap conditions, studying how the underlayment and underlying structure behave when tiles are missing, and whether the new attachment system keeps tiles stable under both ascent vibrations and atmospheric loads during re-entry. The Falcon 9 fairing still experiences a real operational environment, intense launch, vibrations, pressure, changes, mild re-entry heating, separation events, free fall, and recovery at sea. Afterward, SpaceX can perform detailed post-flight inspections, looking for adhesion loss, micro cracks, discoloration, or other subtle forms of damage. The biggest advantage here is iteration speed. Falcon 9 flies often the cost of adding experimental tiles is relatively low, and the risk is minimal. If a tile fails, the fairing itself is not endangered. Meanwhile, the data returns quickly and can be fed straight back into the Starship program, accelerating heat shield development without slowing down commercial launches. This is a textbook example of SpaceX's philosophy: test early, test often, and test cheaply, using an existing reliable platform to support a much larger and more complex system. If these tiles return in good condition, it would not be surprising to see more Falcon 9 missions carrying experimental Starship heat shield hardware in the near future, especially as SpaceX moves closer to Starship Flight 12 and increasingly demanding missions, where heat shield reliability will be absolutely critical. Of course, SpaceX isn't the only company making real progress with its launch vehicles. Its main competitor, Blue Origin, is now taking a very meaningful step forward as well. Jeff Bezos' company has just announced a major milestone in the New Glenn program. The next flight, known as NG-3, will reuse a booster that already flew successfully on NG. 2, marking the first true orbital booster reflight in Blue Origin's history. According to the official announcement on January 22, 2026, NG-3 is scheduled to launch in late February 2026 from Launch Complex 36 at Cape Canaveral Space Force Station, Florida. The booster in question, aptly named Never Tell Me. The odds previously flew on NG-2 on November 13, 2025, when it successfully delivered NASA's Escapade, Mars probes, onto an interplanetary trajectory before making a controlled landing on the drone ship Jacqueline. That alone was a major achievement, but this reflight is even more important. For context, New Glenn's first mission, NG-1, in January 2025, successfully reached orbit with a Blue Ring Pathfinder payload, but the booster was lost during landing. This upcoming reflight therefore represents a clear leap forward in booster recovery and reuse a core design goal for New Glenn, which is intended to fly at least 25 missions per booster. More importantly, this puts Blue Origin firmly into the reusable orbital booster club, and potentially ends a long-running joke from Elon Musk, who has often teased Blue Origin for not putting payloads into LEO due to early delays and imperfect first flights. If NG-3 succeeds, that joke officially expires. Even respected rocket analyst Scott Manley acknowledged this shift. In a post on X, he wrote, "This will use the flight-proven booster from NG-2, and we'll have to stop joking about Blue Origin not putting any payloads into LEO." It was a light-hearted but fair ceasefire statement, because NG-2 already proved that New Glenn can not only reach orbit, but deliver high-value scientific payloads like Escapade onto deep space trajectories.